So hello, my name is Naomi Rowe-Gurney and I am a postdoc at the Goddard Space Flight Center at NASA. I'm very excited to talk to you today about JWST and what it's going to see when it looks at the giant planets Jupiter, Saturn, Uranus, and Neptune. So what is the JWST? The James Webb Space Telescope is an orbiting infrared observatory due to launch very soon. It has a 6.5 meter primary mirror made of 18 separate moving segments and 4 scientific instruments housed at the back of the mirror. It also has a tennis court sized 5-layer sun shield. And all of this is going to be stuffed into a rocket, launched into space, and it's going to slowly unfold itself as it approaches its home at the L2 Lagrangian point. So it's big, it's complicated, it's also the future of astronomy because it's going to be the premier observatory of the next decade, serving thousands of astronomers worldwide. Building it has already been an international collaboration between NASA, ESA, and the Canadian Space Agency. So what makes it so exciting? The easiest way to explain Webb is by directly comparing it to the world's favorite space telescope, Hubble. So for telescopes, bigger always means better, and the animation here shows the relative size of the JWST in comparison to Hubble. And the person there for scale shows just how huge both of these observatories are. And the larger 6.5 meter mirror on JWST means it has more collecting area, which means it can look at dimmer, smaller, colder, and more distant objects than its predecessor. Another major difference between the two is that Hubble has wavelengths mostly in the visible range, whereas JWST has capability from 0.6 microns through the near-infrared to all the way out to the mid-infrared at 28.5 microns. And that's more towards the ranges of the recently decommissioned Spitzer Space Telescope. So it has imaging and spectroscopic capabilities across its whole spectral range using its 4 instruments. The near-infrared camera, or NIRCam, the near-infrared spectrograph, or NIRSpec, the mid-infrared instrument, or Miri, and the FGS NIRIS instrument. And for the giant planets, NIRSpec and Miri are the ones that we're most excited about, specifically because they have something called an IFU, or an integrated field unit. And an IFU gives an instrument combined spectrographic and imaging capabilities. And that means that every single pixel in an image will also have an associated spectrum that we can analyze. And these pixels that are also spectrum are named spaxels, which is fun. So compared to Hubble and Spitzer, we have capability of increased sensitivity, increased spectral coverage, spectral resolution, and spatial resolution. So Webb has 4 major science themes. The first one, first light, is to look back over 13.5 billion years to see the first stars and galaxies forming in the early universe. The second one, galaxies, helps us to understand how galaxies assemble over billions of years. The third one, we can see through the dust to look at where stars and planetary systems are being born. And then the fourth one is planetary systems like our solar system, and also the origin of life. And that fourth one is the one that we're interested in today. So conducting solar system science is actually more difficult than it sounds for a telescope that's primarily designed for distant objects, like galaxies, for example. Galaxies are dim and also relatively stationary on the night sky. And that means that everything in comparison in the solar system is extremely bright and also fast moving. So engineers had to overcome these obstacles to make solar system science possible. And that meant making sure that Webb can move to track objects moving quickly and to make sure instruments don't break when they look at something bright. And this means that Webb can observe everything from Mars out. So that includes moons, asteroids, Kuiper Belt objects, and comets. I'm going to be focusing on the giant planets themselves, so only Jupiter, Saturn, Uranus, and Neptune, and not their moons, which we'll also be looking at. But Webb will look at all 4 of these planetary systems in the first 12 months of operation. So let's start with Jupiter. Jupiter is the largest and one of the most challenging objects to observe with JWST. And that's because it's so big that scientists will have to mosaic multiple images together to get an image of the whole planet or of different parts of the planet. And it's also extremely bright. So actually this mosaicing also helps us to not saturate the detectors because we're looking at smaller parts of the planet. And infrared is also extremely useful for looking below the clouds and the haze to see into the deeper structure of the atmosphere. So the first science that we'll be conducting for Jupiter, we're going to characterize Jupiter's cloud layers, winds, composition, temperature structure, and even its auroral activity. And we'll also be able to determine the 3-dimensional temperature composition and aerosol distributions inside the Great Red Spot. So what about Saturn? The goals at Saturn are actually quite similar, but again, these different wavelengths help us to probe different depths. And following Cassini, so the 2017 conclusion of the Cassini orbiter mission, the goal of Webb will be to establish a baseline for continuing these observations of the planet and the rings, and also the moons. It's going to also enable cross-calibration with Cassini and will fill, hopefully, a wavelength gap between the VIMS and the SIRS instruments. So again, we're going to have to use mosaicing to take images of features like we did with the Great Red Spot at Jupiter. We're going to have to do the same with Saturn, especially Saturn's famous North Polar hexagon, to be able to understand more about it and its extremely exciting circulation patterns. So my favorite planets are the ice giants, and I think that the most exciting science is going to come from them. We've not actually visited since Voyager 2 in the 80s, and most mid-infrared observations are from ground-based telescopes, which means overcoming the difficulty of the atmosphere being in the way. And space-based mid-infrared telescopes like Spitzer are too small to even resolve their disks, so we don't get any images from them. So the JWST is going to blow our current science, ice giant science, out of the water. It's almost like the JWST was made for ice giant science. So that middle image shows the Miri instrument field of views for the different IFUs that show how perfectly both of these planets can be mapped. So the goals in the first 12 months are hopefully to create global maps of both planets and do full chemical inventories, and also to be able to compare the planets directly to understand what makes them so different from each other and different from their cousins, the gas giants. So mid-infrared is particularly useful at the ice giants. Here's some examples of images of Uranus from visible through to the microwave. And we can also apply this to Neptune. This is generalized. So these different wavelengths are sensitive to different depths in the atmosphere. So on the right, this physical structure of an ice giant atmosphere, and it shows the stratosphere and the troposphere separated by the tropopause, and we see where each of these wavelength bands senses. The visible and the near infrared in purple and blue are like the wavelengths that the Hubble Space Telescope looks at, and that senses the cloud tops at the top of the troposphere. Whereas microwave looks deeper into the troposphere, but mid-infrared, that you can see in red there, can see a lot more. It can see the stratosphere and the upper troposphere. So it's useful for sensing where a lot of the chemical reactions take place in the stratosphere, and it can also help us to understand the links between the stratosphere and the troposphere, which the other wave regions can't do. So we can combine these extremely useful wavelength bands with the ability to spatially resolve the planets, and that means that we can do science that we couldn't do before. It's unlike anything we've done before. So this is an example of what we might see at Uranus in 2022 from JWST Miri from the IFU. We've already started the modeling process for future papers and also for application to the real data when it starts to come in. So for each image we take using this Miri IFU, or the medium resolution spectrometer, every pixel in the bottom plot will have an associated spectra like at the top. So we'll be able to look at how the planet looks different in different places and why it's looking different in different places. So where is the JWST now? It's currently at the Kourou spaceport in French Guiana, being prepared for launch. And when I do this talk live, it will be extremely close to launch. And once it's launched, it'll unfold on its way to the L2 Lagrangian point, which is 1.5 million kilometers away. It'll take about 2 months to reach that L2 location and also cool to operating temperature. Then around 4 months to do alignment, checkout, and calibration before the science can start. And for example, the ice giant will be looked at around summer of 2022, we hope. So thanks so much, and follow me and the telescope on Twitter for updates in coming months, and I'm looking forward to your questions.